Surprised not more people are showing up.
Yeah,
Accelerated class.
I'm surprised too, since more people said they were going to show up. All right, doesn't matter. Let's go for it. So Calc 1, there are 3 primary topics that I want to discuss with you. And the second and third are related to the first. It's just kind of an application of the first. The first one is limits. Okay, that's a topic you spend a couple weeks on in Calc 1 or a couple days in the summer. All right. Then we have derivatives, which we spend many weeks on in Calc 1, talking about what it is, methods, and then applications and fun problems like related rates and optimization and all that stuff. And the third is integrals, which includes antiderivatives. And so we'll take these one at a time and go into some depth. So let's begin with the limits. And so when you take a Calc 1 class, depending on who your instructor is, they might give you a very complicated definition of a limit, which includes Greek letters like epsilons and deltas. And you want to make sure that if you're within a certain distance of the x value, then the y value is within a certain distance of the limit. And it gets kind of complicated to write it formally, but intuitively, it's not that complicated. So a limit, this just gives you the height of a graph well, I should rephrase this. Gives the height that a graph, is approaching as x approaches a certain number. Okay. And if the limit, I should say this, if the graph is continuous, then the limit is just equal to the function value. Like, for instance, the limit as x approaches 2 of 2x plus 1. Okay, well, 2x plus 1 is a continuous function. There's no gaps in this thing at all. And so this limit would just be equal to, well, just plug in 2 for x. So it's equal to 5. And so if there's no problems with our function, the limit is equal to the function value. Okay, great. If there are some problems with our function, like for instance, this example here, then the limit might equal a value that is not even defined on our original function. Okay, so in this one, if I just plugged in 2, then the denominator equals 0. And that's a problem. We don't like that. However, the numerator also would equal 0. And we get 0 over 0 if you plug it in. That is known as an indeterminate form, which means that there's more that can be done to actually evaluate this limit. And in particular, what can be done is that we can factor the numerator. It's a difference of squares, so that's going to be x minus 2 times x plus 2. Okay, still problems if I plugged in 2. But now we can cancel out this stuff here. And so the limit as x goes to 2 of this function is equal to the limit as x approaches 2 of the function x plus 2. By the way, that does not mean that this function here is equal to x plus 2. In fact, it isn't. Because x plus 2 is defined at x equals 2, whereas this function was not defined at x equals 2. And I'll show a picture of that in a second. But then we can just plug in 2 because now there's no problems. And so the limit here is equal to 4. Okay, just to kind of show that in another way, let's go over here. If we were to graph that, so y is equal to x minus 2, x squared minus 4, compared to x plus 2. I mean, they look practically identical, right? I mean, the blue line is just covering the red one. However, they're not identical because if I went to x equals 2, in this first one, it tells me that it's undefined. But if I go to x equals 2 in the blue one, it is defined, it equals 4. So they're not the exact same function. However, the limit as x approaches 2 is the same because the height of the graphs are the same at that point. Okay, and while this is fine, what we care more about in this class is going to be limits when x goes to infinity, especially in the second half of the class. So the limit when x goes to infinity, this is just looking at how does this graph behave at the extremes? Like, what is this thing converging to as x gets huge? And so let's do an example like x squared e to the minus x. All right, well, with that, this limit does exist. We can rewrite this as the limit of x squared over e to the x as x goes to infinity. That's just by exponent properties. If you have a negative in an exponent, you can put it in the denominator. And now if I think about what happens when x goes to infinity, well, the top we're going to have infinity squared. That's infinity. On the bottom, we have e to the power of infinity. That's infinity. And so infinity over infinity, what does that equal? It depends. It could be literally anything. That's another indeterminate form. And so we can use the trick that we always teach is L'Hopital's rule. And we haven't talked about derivatives yet, but you probably remember how to take derivatives of these easy functions. It says that all we really care about is which one is getting to infinity faster. And speed is a derivative. And so if I take the derivative of the top function over the derivative of the bottom function, and of course we know e to the x is its own derivative. It's very special that way, only function that is its own derivative. Okay, well now this looks simpler, although we still have the same problem, infinity over infinity. So we can use the L'Hopital's rule again, take derivatives again of the top and the bottom, and we get 2 over e to the x. Okay, but now the top is not going to infinity. We get 2 divided by e to the infinity, essentially, which is 2 divided by infinity, and a finite number over a number that's going to infinity. Well, denominator is getting bigger and bigger and bigger, so this whole thing is going to 0. Would be that limit there. Okay, so we care about which function is growing faster. And so it's nice to know the speed at which functions grow. And so I'll mention some of the stuff here. So constant functions are slower than natural log or log functions. Yeah, let me say is instead of are, which is slower than linear functions, is slower than something like x squared, is slower than polynomials with a higher degree than x squared, which are slower than exponentials like e to the x, is slower than factorials. If you don't know what factorials are, we'll talk about them later in the course. So this is the progression there. So we have constants, natural log, linear, quadratic, other polynomials, e to the x, and then factorials. And so if we know that progression, then these problems can become much simpler. And so if we have like x to the 4th over x cubed times the natural log of x. It's like, okay, well, we could do the L'Hopital's rule several times here until we don't get infinity over infinity. Or you can just kind of think about, well, x to the 4th, that's bigger than x cubed, of course, but this natural log is kind of playing a part here. But we can kind of divide this into x cubed times x on top over x cubed times the natural log of x. And we know that x grows faster than the natural log of x, which means that the top is going to grow faster than the bottom. And so this whole thing is going to go to infinity without having to do 4 L'Hopital's L'Hopital rules here, or however many it would take. Okay, but then what if they are growing at the same speed? Like what if we had x cubed, like 4x cubed minus 2x over x squared minus x cubed, let's say 3x cubed. Okay, well, the top and bottom are both going to infinity, or at least infinity or negative infinity. But all we really care about is the highest degree term. They both have the same degree in the top and the bottom. The largest power is 3. So they're growing at the same speed. And so what we would do here is either L'Hopital's rule 3 times, or just realize that since they're going at the same speed, we would just divide the leading coefficients of both of those polynomials. So 4 is the coefficient of x cubed on the top, -3 on the bottom, so we just divide those. That's our limit. And by the way, this is also known as a horizontal asymptote. We talked briefly about vertical asymptotes on Tuesday. And this is how a horizontal asymptote is defined. What value is the function approaching as x goes to infinity or negative infinity? Okay. Questions about that limit stuff? Okay. Then let's move to derivatives, which are also limits. So derivatives, these things, pretty useful. These give the slope of a curve at a single point. Another way to say that is that these give the instantaneous rate of change at that point. Okay, so they give the slope of any curve at a single point. Although we're familiar with the slope kind of only when it comes to linear functions, because with linear functions, y equals mx plus b, m is the slope. And so it's right there in the equation. But with quadratic functions, for instance, ax squared plus bx plus c, there's no slope here. And that's because with a quadratic function, that slope is constantly changing. Like right here, the slope is 0. Over here, the slope is 1. Over here, the slope is 4, and et cetera. And so it's always changing, as opposed to a linear function, which has the same slope no matter where you are on the curve. But we can still take the idea of what we know about a slope for a linear function and kind of apply it to other functions. And so remember that if you know 2 points that a curve goes through, a linear curve, you can find the slope by taking the change in y over the change in x, which we often say y2 minus y1 over x2 minus x1. Okay, I'm going to name these slightly differently. So instead of y2, I'm going to say that's f of x2, because that's the same thing, and f of x1 over x2 minus x1. Okay. So we're going to take this idea and we're going to apply it to functions that aren't always just a straight line. And so let's look at an example where we have a curve that looks like that. Okay, it's not straight. And let's say that we want the slope at this particular point right there. Well, because my drawing skills are lacking, I'm going to go to Desmos here to show this. Okay, so here is, here's a curve that is similar to the one I just drew. It's not a straight line. And let's say that I want to find the slope exactly at this point A. Okay, so one thing that I could do, at least to get an estimate for the slope, is to use another point like B and basically do y2 minus y1 over x2 minus x1 to get the slope. And if I did, then I would get that line right there. That connects those 2 points. It has the slope using that. But that is not the same as the slope of this curve exactly at this point A. Okay, at that point A, it would actually be this slope. As you can see, it matches up quite nicely with like the way that this thing is curving at the point A, this black line. And so the question is, well, how can I make this blue line a better approximation of my black line? And what we can do is, well, let's not use the point B. Let's use a closer point, like the point C, right? If we did, well, now this is my approximation, which is a little bit closer than it was before, right? To the black line. Well, why stop there? Let's continue to move it closer until we get to the point D, and it's looking better. But let's keep moving it closer. Okay, point E, even better. But why stop there? So if I make this closer and closer and closer, the second point, then my blue line gets closer and closer and closer to the black one. And so what's the optimal distance between the 2 points to make it the blue line equal the black one? Infinitely close. Yeah, okay, good. So in my little program here, I have 0. But 0 doesn't really make sense because what we're doing is on the bottom, it's x2 minus x1. And so if the distance was 0, that means that the 2 points would be identical. And that means that we're dividing by 0. So we don't want it to be 0, the distance, but we do want it to be infinitely close to 0. And so let me just label a few things here, like this is x1, and if this is x2 over here, I'm going to think about what happens when I move x2 as close as possible. This is a different color. As close as possible to x1, right? And then I can basically do y2 minus y1 over x2 minus x1 to connect these with a straight line, essentially. Okay, so we don't want them to be the same point because then we divide by 0. We want them to be infinitely close. And so the way that we can write that is that the slope at x1 is going to be the limit as x2 approaches x1. Right? That will make it infinitely close. And then it's the same idea, f of x2 minus f of x1 over x2 minus x1. So that's one way to write the slope. This gives the derivative. This is the derivative at x1. The more common way to write this is to think about this horizontal distance between the 2 points and call it h for horizontal distance. And if I call this just x instead of x1, then this second point would just be x plus h. And then I would have the limit as h goes to 0, that horizontal distance going to 0, of f of x plus h minus f of x over h. And that is the traditional way to write the derivative of x. Right? And then in a Calc 1 class, you take a while to use this definition all over the place, right? Before you learn about tricks for these derivatives. And so just really briefly, if we want to find the derivative of f of x equals x squared, we can do that. So then f prime of x would be the limit as h goes to 0 of x plus h squared minus x squared over h. So then foiling this out, I get an x squared plus 2xh plus h squared minus x squared all over h. And I want the limit as h goes to 0 of this thing. Okay, so I can cancel out the x's because I have an x squared here and a minus x squared over there to get 2xh plus h squared over h. And now I can cancel a bunch of h stuff. There's an h in both of those terms on top, so that cancels, the squared cancels, the h is gone on the bottom, which means that it's the limit as h goes to infinity of 2x plus h. I have nothing on the bottom that's making me divide by 0 anymore. I can plug in 0 for h and I get 2x. Okay, so you use this definition, I don't know, a few days, a week, and then you're like, well, that's really annoying to use that definition every single time. And so it's much nicer to learn a couple of rules for derivatives. So I will put them here. So this is just from the memorization sheet. And we go through a bunch of different rules for common functions, like the derivative of a constant is 0. We just saw this one in action. The derivative of x squared was 2x. So basically the 2 came down in front, and then we subtracted 1 from the power. E to the x is its own derivative, super nice. And then there's all these other ones as well. And then we also have some rules for taking derivatives of product, quotient, and composition of functions. And so let's go through a couple of examples using those and using some of these properties. So example, find derivative of number 1. Let's say that f of x is equal to 4x squared e to the x. Number 2, let's say that g of x is equal to the natural log of x over sine x. And then number 3, let's say y is equal to the arctangent of secant of x. Actually, let's make it more complicated. Secant of negative 2x. Okay. So let's find these derivatives. Number 1, so when we have f of x equals 4x squared times e to the x, let's call, well, obviously we have a product of functions here. We have this one here times that one. And so it's traditional to call these things u and v. Don't have to, but we can. And the product rule says that the derivative of the function is the derivative of the first times the second plus first times the derivative of the second. So using the power rule for this one, well, the 4 is a constant, it just kind of hangs around for the ride. X squared, the 2 comes down, multiplies by the 4 to get 8 times x times e to the x. Then we add to that 4x squared without a derivative times the derivative of e to the x, which is still e to the x. And that's it. That's the derivative. We can simplify it. Like I can factor out a 4x e to the x and be left with a 2 plus x. But that is our derivative. Okay, for number 2, here we have a quotient. We're dividing two different functions. And so this is often, again, called u and v. And then g prime of x would be u prime times v minus u times v prime all over v squared. And so the top of the quotient rule is just like the product rule, except there's a minus instead of a plus. So here the derivative of u would be the derivative of the natural log of x, and that is 1 over x, times the denominator is sine of x, minus the natural log of x times the derivative of sine of x, which is cosine of x. And we divide that by the denominator squared. So that's fine. Or we can simplify this a bit with, properties of fractions. We would get something like this. Times cosine of x all over x sine squared x. Okay, and then we have that third one, which has a function inside of a function inside of another function. We have y equals the arctangent of the secant of negative 2x. And so this is going to be a chain rule. And the way that I like to think about the chain rule is by actually forming a chain of derivatives. So I'm looking for dy dx, right? That's another way to write the derivative, it's like the change of y over the change in x. Well, I can rewrite that as something like dy du times du dx. If you stare at that for a second, you can see that that's the same thing, because I could, cancel out these du's and be left with a dy in the numerator and a dx in the denominator. But I don't want to cancel them out. I'm going to leave them like that, because this new function u is going to be a kind of a gateway to performing this, this chain. So u is going to be the inside function. So I'll say that u is equal to the secant of negative 2x. And then y I can write as the arctangent of u. So then I just want to take the derivative of both of these pieces individually and then multiply them together. So dy du is going to be, well, the derivative of the arctangent of x is 1 over 1 plus x squared, which means that the derivative of the arctangent of u is 1 over 1 plus u squared. Okay. And then here I want to find du dx, the derivative of this function with respect to x. And within this, I have yet another chain rule. So I can say, well, I'll call this thing v. So du dx would be equal to dv. Let's actually do this. Du dv times dv dx. And so that just means take the derivative of the inside which is -2. That'd be this part right there. And multiply that by the derivative of the outside. And the derivative of secant of something is secant of that something times tangent of that something. So this would be, I'm kind of running out of room here. So that would give me secant V times tangent V times -2. So that is this part, and this is that part. So then overall we have dy dx is going to be dy du times du dx, which is 1/1 plus u squared times all this stuff over here, times secant v tangent v times -2. And then cleaning all that stuff up. And I don't want to be left with v's and u's everywhere. So I need to replace some stuff. So on the top, I have a -2. I have a secant of v. Well, v was -2x. So I can plug that back in. Times tangent of v, which is tangent of -2x. All over 1 plus u squared. And u is the secant of -2x. So we get 1 plus secant squared of -2x. So that is our answer. And those become much easier with experience because you can kind of do some of that stuff in your head. Just like find the derivative of the inside function, that's -2, times derivative of secant, that's secant tangent, times the derivative of arctangent. That's all we really did. We just multiplied all those derivatives together. Any questions on those 3 examples? All right. And so we will talk about integrals here as well. Calc 2 focuses a lot on integration. And so we're not going to get too in depth or like too advanced into integrals in this review because we have a couple weeks of class for that. But I want to go over what you should be familiar with coming into Calc 2. So integrals, there's 2 types of integrals. There are indefinite integrals and there are definite integrals. 2 types. Definite and indefinite. And in Calc 1, you focus a bit more on the definite integrals. Let's begin there. A definite integral just means that we have this integration symbol and we have bounds on it. And what we want you to know is that this here gives the area under the curve of f of x from A to B. So if I have a little picture here and I have this function f of x, so this is x, this is f of x. Then this definite integral is going to give you the area under the curve. And when I took calculus, I was taught that and I learned it and I remembered it, but I didn't know why or how those things were connected. Just like, okay, fine. I'll do what you tell me to do. So I'll go a little bit into how these things are connected. And we'll start with an example with a very simple question. If you drive 60 miles per hour for 1 hour, how far did you drive? Crazy. What do we think? No, it doesn't depend.
60 miles.
Yeah. If we're driving exactly 60 miles per hour for exactly 1 hour, then it's going to always be 60 miles. Don't need that. Yeah, 60 miles. That's the answer. That's correct. There was an old YouTube video where some guy like asked his girlfriend that, and she was just struggling with.
I saw that.
Okay, so drawing a picture of this. So if we have time over here, we have speed over here. And we're going, 60, and we have 1 hour here. If we're going 60 miles per hour, that's a constant function, right? It's just going to be a straight horizontal line. And really, the idea here is that to figure out how far we went, we multiply the speed by the time, which was 60. And turns out that that's exactly equal to this area, right? Because this is just a rectangle with a height of 60 and a base of 1. And so this is 60 miles is the area of that rectangle that we just did. And so a more difficult question is, well, what if I don't go a constant 60 miles per hour? What if I start at 0 miles per hour and then I very slowly increase my speed constantly for 1 hour until I'm at 60 miles per hour? Okay, so I still have 1 hour that I'm driving. I'm going to get to 60 eventually, but my curve looks like that. Okay, I'm very slowly accelerating. Well, we can still visualize that with the area under the curve. And so this area here will give me how far I went. So the question is, what is that? Well, now this is another nice simple shape. This is a triangle. And so the area is the distance traveled, 1/2 base times height, which would be 1/2 times 1 times 60, which is 30. And so I've gone exactly 30 miles if I slowly ramp up my speed instead of being at a constant speed. And those aren't too bad to find how far you went, because both of those are very simple functions. Straight line, straight line. It gets much more complicated when we have a more realistic pattern, right? So we start at 0, we accelerate, we get slowed down, we stop at a traffic light, we go back up. All right, so like, how far did I go in this time? Well, it's still area under the curve, but now the question is, how do I get the area under that curve? And the way that we can do that is by using a bunch of different little rectangles and then add them all up. So if I think about like, well, I'm going to use this little rectangle to estimate the area there, and then this one to estimate it there, and then this one and this one. And if I just keep doing that and then I can think about adding up all these rectangles. I'll just draw a couple more. Okay. So let's say that we have this sort of picture happening, and we want to know the area under the curve. And let's say that this right here is time 1. That's all I really care about. Well, I can think about the base and the height of each of those rectangles, because the area is going to be base times height. And so for the base, I can just think about some small amount of time, which I might call like delta t. Just the change in time between the previous rectangle and my current one. And then the height of these rectangles, well, that will be whatever the function value is there, whatever your speed was at that little snapshot in time. So we might say like f of t, but to distinguish between like this height and this one over here, let's put a little subscript on that. So like this might be like T20, this might be like T10, this would be T1 over there. And so then the area under the curve, which is representing how far did you actually travel, it would be approximately equal to the sum of all of those rectangles areas. And the rectangle's area is f of ti times delta t. And if we have n triangles, or sorry, n rectangles, then we would add it up from I equals 1 to n. Okay, and we can think about doing this. I have a picture of this as well, although it doesn't match the one I just drew. That's fine. So if I did this with one rectangle, and I wanted to estimate the area under this curve right here, for instance, don't worry about all this stuff on the left, but then it's not going to be a very good approximation. Like I'm overestimating here, I'm underestimating here, but I'm going to overestimate more than I underestimate. It would be better if I took more rectangles. So if I did 5, okay, that looks like a little bit better approximation of the area under that curve. If I did 9, that's even better. If I keep increasing the number of rectangles that I'm taking the areas for and then adding them all up, then I'm going to get closer and closer to the actual area under that curve. Okay, so with 100, maybe it looks pretty good. If we zoom in, then we can still see, oh boy, we're missing stuff here, we're overestimating it there. So the optimal number of rectangles to add up is an infinite number. Okay, but adding up an infinite number of anything is kind of difficult and time consuming. But that's the idea, is that the area is approximately equal to the sum of these finite number of rectangles areas, but the area is exactly equal to this same thing if we had infinitely many rectangles. So we want to take a limit as n goes to infinity of this sum. And that thing, the limit as n goes to infinity of a sum from I equals 1 to n, instead of writing that every single time, this is defined as the integral symbol. And we're going to put the lower bound on the bottom, which is 0 in our case. We'll put the upper bound on the top, which is 1. We'll have a function of t. So we'll just put f of t without that subscript I. And delta t, that change in time, well, if we're doing an infinite number of rectangles, then the distance between, each spot where we're starting the rectangle is going to go to 0. But we don't write 0, we write dt, which represents a very infinitesimal distance or change in time. And so that is in how the definite integral works. And this is defined, well, I guess I should say this. We can evaluate that using antiderivatives. Turns out that this is equal to capital F of 1 minus capital F of 0, where the derivative of capital F is equal to lowercase f. Or in other words, capital F is the antiderivative of your original function lowercase f. And this is famous, crucial. You might even say it's fundamental. This is the fundamental theorem of calculus. This idea here, that we can evaluate definite integrals using antiderivatives. Okay, and since we can evaluate definite integrals using antiderivatives, we use the same symbol, this integration symbol, to mean an antiderivative if there's no bound on it. So just really quickly, an indefinite integral is an antiderivative, the opposite of a derivative. And that would just look like integral f of x dx. No bounds. It just means find the function that has a derivative equal to the function that's in the integral. Okay. And so for you coming into Calc 2, I don't need you to know integral techniques. I don't even need you to know substitution, although I'm pretty sure that you learned that one in Calc 1. We're going to review it again in Calc 2. And we're going to continue first couple of weeks of doing a whole bunch of different integration techniques. But what I do want you to know is basically the opposite of this chart for derivatives, right? Like I know that the derivative of the sine function is the cosine function. So we need to know that the antiderivative of the cosine function is the sine function. And that's what this is down here. So we have all of these, which is basically just that other part that I put in the notes earlier in reverse. Okay. So just a couple things on this. First of all, you'll notice that there's plus c's everywhere. And for any indefinite integral that doesn't have bounds, we need to put a plus c because we don't know if there was a constant, like any function that has a derivative equal to sine of x, for instance, could be negative cosine x, but it could have been +1, it could have been +0, it could have been +20. We wouldn't know because that constant derivative would have gone to 0. And it wouldn't be represented inside of this integral. So they all have plus c's. Otherwise, it's just the opposite of that chart. And so like the integral from, well, let's do an indefinite one first. So the integral of 6x to the 4th dx, we're looking for what function would give me a derivative equal to 6x to the 4th. And so using the power rule in reverse, we can use this up here. In our case, n is 4. And so we're going to keep that 6 around. We need to divide by 4 plus 1. And then x gets the new power of 4 plus 1. And we need to add c to it, which is the same as 6 over 5 times x to the 5th plus c, where c is any constant. All right, then we can also do something like the integral of 2x minus e to the x from 0 to 2. And now that this has bounds on it, we can use the fundamental theorem of calculus, which says take an antiderivative of the stuff in here and then plug in the bounds and subtract. And so the antiderivative of 2x, well, the new power in x has to be 2, and we divide by the new power. So we get just x squared. The antiderivative of e to the x is e to the x. How nice. And now we need to evaluate that at 2 and 0 and subtract those. And the way that we typically write that is with a straight line, 2 on top, 0 on the bottom. So I'm going to plug in 2, I get 4 minus e squared. And then minus, plug in 0. 0 minus e to the 0. Simplifying that, that gives us 4 minus e squared and minus a negative e to the 0. E to the 0 is 1, so that's the same as plus 1. Equals 5 minus e squared. And that's approximately equal to, let's see, 5 minus e squared, negative 2.389. And it is okay for the area to be negative. Negative area is area below the x-axis. So if I plot that 2x minus e to the x, y equals 2x minus e to the x, you can see that it's all below the x-axis. So we found the area between 0 and 2. So we basically found this area between the x-axis and this curve. And it's all below, so it's all going to be negative. There we go. Antiderivatives. Any questions or comments about that?
Makes a lot more sense than digging it over.
Oh yeah, just to get the big picture really quickly thrown at you. Yeah, so I think that's all I really wanted to say about this stuff. I mean, we did 3 courses in 3 days, so there's a lot I didn't cover, of course, but hopefully that's just about everything you need coming into Calc 2. And so you can work on, like I said before, you can work on practice problems that are in the review or the day 1 worksheet that I gave you. You can work on memorizing the stuff on the memorization sheet, but I'll talk more about that when we officially have class next week. So see you on Tuesday, next door, that classroom, and have a nice 4th of July weekend.